Alright team, so we're back. Let's bring it home with our last couple of concepts here. Concept 1.3 talks about how when we're studying biology or just nature in general, scientists are making observations and then they're using those observations to form what's called a hypothesis. And then their experiment is basically the test for that hypothesis. It goes into a little bit of history or background as far as some of the terminology. The word science is actually derived from the Latin word that means to know. And so we are doing science to learn more about the universe around us. And we're using inquiry. Inquiry is basically the process of curiosity to work to learn more information about the world around us. And that whole process includes making observations with our five senses. What do we see, hear, smell, touch, taste? What do we think about that? What are some predictions that we can make using that information? And then how can we test to see if those predictions are actually true or accurate? So biologists, of course, are studying natural structures and processes and using this type of inquiry to learn more about the natural world of living things. So when they're doing that, they're collecting what we call data or data. That's the actual recorded observations, again, using those five senses we talked about. We can define data basically into two camps. It kind of falls into two camps. One of those is called qualitative data, or descriptions, and one of those is quantitative data, which is generally numbers, recorded information. A good example is, say for example, naturalist Jane Goodall. She has studied chimpanzees in Africa pretty much all her life. She's very well known for that. The vast majority of data that she collected would be what we would call qualitative data. So when you look at her notebooks, it's going to be filled with drawings and descriptions of the chimpanzees and their behavior and the way they look and the way they act. And it's pretty much qualitative data, descriptive type data. On the other hand, we have someone like Neil deGrasse Tyson, astrophysicist Neil deGrasse Tyson, who is the head of the Hayden Planetarium in New York City. Also very well known, tends to show up on a lot of cool TV shows like Big Bang Theory or The Daily Show or Colbert. When you are an astrophysicist, you don't really have the ability to go out with a notebook and study firsthand most of what you're looking at. So, for example, when Neil deGrasse Tyson is studying black holes in space, he's going to use numeric data and measurements. And most of his data is going to be in the form of tables and charts and graphs and numbers. And that would be considered quantitative data. Both of these are important parts of science. They're just two slightly different ways of gathering information about the world around us. Continuing with our theme of twos, let's talk about the two types of basic reasoning that goes into developing these hypotheses. One of these is called inductive reasoning. Inductive reasoning is kind of going from the trees out to the forest. In other words, you're looking at particular instances or specific observations, and then you're kind of making a generalization from those observations. So, for example, the specific observation may be that the sun rose in the east or in the same place every morning that you've recorded from Sunday, Monday, Tuesday, Wednesday. Let's say you recorded where the sun rose or the direction that it rose for the last 3 months. Well, those are specific observations. From that information, you might be able to lead yourself to the generalization that the sun always rises in the east. So going from specific observations to a generalization from the trees all the way out to the forest, that's called inductive reasoning. The other side of the coin is deductive reasoning. Deductive reasoning is going from the forest back to a single tree. So you might be using a general premise or idea to make a specific testable prediction. So the example the book gives is if organisms are made of cells and humans are organisms, then humans are composed of cells. That would be your deductive prediction, and that's something that could be tested. So when we do this inductive or deductive reasoning, we're going to be forming what we call hypotheses. And hypotheses are basically our explanations, our temporary explanations, or our proposed explanations to our problem or our question. They're not necessarily perfect ideas at this point, but they're something that can be tested. I know in elementary school, oftentimes in middle school, even in high school, they call them educated guesses, an educated guess, and that's probably a pretty good way of describing them. But perhaps a tentative or hypothetical explanation is perhaps a little bit better way of describing what a hypothesis is. So when we get that hypothesis, we're going to lead to a prediction that can be tested. And so, for example, in the textbook, they talk about this campground type prediction here of regarding your flashlight. So let's say you have a flashlight. Your observation at the top, of course, is, hey, my flashlight doesn't work properly. So that leads you to a question as to what is causing that problem. And then you might develop two competing hypotheses to answer that question. One of them could be that the batteries are dead. The other one could be that you have a burned out bulb. And of course, that is a prediction that leads to a prediction that can be tested, and then that test will either help confirm or deny one of these potential hypotheses. Now, an important thing to remember is that failure to show a hypothesis false does not prove that hypothesis. That's a little bit confusing sounding, but their example helps clarify. So, for example, let's say that you believe the flashlight bulb is the problem, and so you replace that bulb, and now the flashlight works. Well, you may say, hey, that proves my hypothesis was correct. Well, in actuality, it doesn't necessarily prove it was correct. It may disprove the idea that it was the batteries that was causing the problem, but there could be other things that are related to your flashlight bulb. Like, for example, perhaps the first bulb actually was working, but it wasn't making good contact, or it was installed incorrectly the first time. So your hypothesis, just because it didn't come out to be false, just because it seems to be supported, it doesn't necessarily prove it with any sort of absolution. Some people take this inability to provide absolutes as a weakness of science, but it's really kind of the wrong way to think about it. Science deals in probabilities. So, for example, if I my computer mouse and I hold it up in the air and then I let it go, well, it's very probable that it's going to fall to the ground. That observation or that hypothesis is based on many observations and tests to kind of prove that idea. But it doesn't mean that I can say forever that always 100% that the mouse will fall to the ground when I release it. There's no way to definitively prove that with absolute 100% certainty. So science doesn't deal in 100% certainties. Science deals with observations that lead to generalizations that can be strengthened by repeated analysis and experimentation. But that doesn't mean that tomorrow things might be different. And if we learn new information, we change our thinking to try to build a consistent model of the world around us. Another important thing to remember is that a hypothesis must be testable and falsifiable. There must be some way to show that the hypothesis is not correct or is not supported by the data. So if you said your flashlight didn't work because there were little wood elves or ghosts that were fooling with the flashlight and causing it not to work, well, that is a hypothesis, but it's not scientifically testable or falsifiable, so it wouldn't fall under the realm of science. So supernatural or religious explanations for what we see in the world around us, those are outside of the bounds of science. They may fall within philosophy or religion or other types of studies, but if they cannot be tested and falsified, then we wouldn't consider that a scientific hypothesis. Certainly in elementary school, middle school, you probably learned a scientific method. Perhaps it was 5, 6, 7 steps. Your teacher probably taught it to you and said, this is the way that science is done, and you shall not deviate. And of course, as you get into high school and then into college, you find out that that's not exactly the way it is. The scientific method is an idealized process of inquiry, of the way we do science. For a lot of my middle school kids, when I was teaching middle school, I would tell them the mnemonic, people really hate eating dirty carrots. And that was a way for them to help remember these steps of problem, research, hypothesis, experiment, data, and conclusion. But in reality, that's not always the way that science is done. There is a scientific method and a way of going about it, but it's not always 5 or 6 lock steps that can never be changed. Sometimes a good way to learn or study is to look at an example. So in your textbook, I think it's on page 20 through 22, there's a great example of a case study of scientific inquiry regarding mimicry in snakes. You're probably familiar with the fact that there are poisonous snakes that are brightly colored, but there are also non-poisonous snakes that tend to have very similar coloration, and that's an evolutionary adaptation that over time they have developed that helps keep them from being attacked or eaten as much, because in the animal kingdom, for the most part, bright colors tend to be a warning signal or a warning sign, and over time, most of the other creatures will have evolved this adaptive behavior to avoid that color. So, for example, what they studied in the Carolinas was two particular types of snakes, a venomous coral snake and its mimic, the non-venomous scarlet king snake. And in the book, they show this map where, in some cases, both snakes live in the same area and their range tends to overlap. So where you have this stripe pattern here, their range is overlapping. And then where you have only the light tan or light brown, that's where the king snake is, the non-poisonous one, but you won't find the poisonous one in that same area. So what they wanted to study was to see if this coloration of this non-venomous snake right here is helpful. Well, it really should only be helpful in the areas where you find the poisonous snake as well, because otherwise this coloration is less a signal of danger and it's more of a bright sign that's difficult to hide from your predators. So what they did is they did a study to see, is this coloration beneficial everywhere, or is it only beneficial where you find both snakes, where you also find the venomous coral snake? Now, anytime you do a field experiment like this, you're going to have a hard time making sure you control all the variables. So at the very least, you need a control group. So what they did is they built artificial snakes. Here they are right here. At the top, you have an artificial snake that looks like the king snake that they're studying. And then they built some artificial snakes that were the same size, shape, and material, but just a regular brown color, like some sort of brown garden snake or just regular snake you might find somewhere in the forest. Why did they do this? Well, they wanted to make sure that it wasn't the clay, the material, the shape that was causing the attacks or the lack of attacks. So they wanted these two snakes to be exactly the same, except for the coloration. Down here at the bottom, this poor guy, this brown snake, has been attacked, so you can see where he's been bitten and clawed, and that's the type of damage they're going to be looking for to study. So they put these two models of snakes out, and after 4 weeks, they retrieve their data, and then there's a nice graph or chart inside the book that shows their data. So in the areas where the poisonous snake does not exist, that bright coloration was of no use. As a matter of fact, it was attacked more often, probably because it stands out in its environment quite a bit. But in the areas where the poisonous snake does exist, it did exactly what you would think, because it mimics the poisonous snake, and those animals in that area have evolved to adapt their behavior to stay away from that coloration. You can see that the brown fake snakes were attacked quite a bit more than the colored fake snakes that look like the coral snake. So, kind of a cool result where that coloration is advantageous in one environment, this environment over here, and not advantageous in the other environment right here. An important fact to keep in mind is in an experiment like this, especially one done out in the field where you have so many variables that are difficult to control, there's no way that you can control all of the variables except for the one that you're testing. So what you need to do is make sure you have control groups to cancel out those unwanted variables and the effects of those unwanted variables. So that doesn't mean that you have eliminated all unwanted variables, but you've done your best to cancel them out using your control group. And then, of course, if we really wanted to verify this information, we want to repeat this experiment, because in science, if your observations and results are not repeatable, especially by others, well, then the information would become suspect. On to our next phrase here, theories in science. Theory in science is a very important thing, and unfortunately, theory is perhaps the scientific word and concept that is most misunderstood and most misused by the general public. A theory is not the same in science as it is in your everyday general language. Like you might be watching Scooby-Doo and they'll say, well, I have a theory that blah, blah, blah. And there they mean basically just a guess or a hunch not backed up by a lot of information. But in science, a theory is much broader in scope than a hypothesis. It is a general statement that has explanatory power, and it's supported by a very large body of evidence. So for some more information on what exactly a scientific theory is and what that word theory means, you might want to read the uploaded PDF document that I put online that's entitled Scientific Laws, Hypotheses, and Theories. It's got some good information in there, and hopefully the next time that someone says, well, that's just a theory, if they're talking about science and it truly is a theory, you'll know how to respond to that and perhaps how to explain what a theory is in correct terminology. We're going to push on through to Concept 1.4. It's a short one, so we might as well finish up. And it basically talks about some historical background in science, how science is a social activity. Most of the times, or a lot of times in movies and TV, you see this caricature of a scientist, this lone, crazy scientist in his laboratory late at night working alone. But truly, that's generally not the way it works. Science is a social endeavor, and most scientists are working with other scientists and the public and students and other people to get their job done. And that's a good thing, because science is really about building on the work of other people. Every time we discover something new, we are adding to our increasing pile of knowledge. And what we learn today is in part helped by what scientists in the past learned prior to us. One other term they mention here is technology. Some people kind of use the word science and technology as if it were the same. Not exactly. The goal of science is to make discoveries and understand the natural world around us. The goal of technology is to use what science learns and put it to some particular purpose or use. So when you're using your iPhone or you're surfing the internet, that's technology. That's scientific information that has been learned that is then put to use for some particular purpose. And a good way to think about it is biology is marked by discoveries, whereas technology is marked by inventions and products and the like. Finally, they do talk a little bit about ethical issues in science. Science is not a discipline that can make ethical or moral decisions. That's something you have to do in the world of philosophy or morality. So there are a lot of ethical issues that arise from technology and science. I mean, science may be able to tell us this is what we can do, but it doesn't necessarily have the ability to tell us if this is something we should do. So there's a lot of ethical issues that pop up in the use of science and technology that are very interesting, very cool to talk about and discuss with people and get their differing ideas. So as a society, we can decide, should we do everything that possibly we can do with science and technology. Finally, last but certainly not least, the value of diverse viewpoints. Historically, science has been kind of the domain of aristocratic, richer, primarily white men. That's not necessarily a good thing. You want a diverse group of viewpoints, and you want a diverse group of experiences. So because science is a social activity, it's much better if we have a wide range of people involved. And most of our scientific discoveries over the years have been a combination of a wide variety of people from a wide variety of ethnicities and from both sexes and from all around the world. So it's always good, and it's good to see nowadays that it's much more the case that we have a wide variety of viewpoints in science. And that's good, I think, in every field, including the field of science. We're going to stop right there. I hope you guys are learning and progressing well. If you have any questions, let me know. Otherwise, we are done with Chapter 1, and we'll catch back up with Chapter 2. Thanks, guys. Bye-bye.